Okay. Hello. Is is the desktop visible? Does it seem like everything's ready? I'm kind of just arranging my desktop here. Okay, let's see.
Make sure not to mute yourself this time.
Yeah, it's unmuted. It's been unmuted since last time. Yeah. Okay. Okay. I've added more code to this folder on futures. I left the old version of the code up there, and this is new version. I mean, if for some reason you want to compare the latest versions to the ones we looked at last week, yeah, I left them up there. But for the most part, I've updated a lot of the examples to kind of trying to improve the code and make it better. So let me open the folder that has that code in it. Okay. When we left off last time, we were working with I know we did, I think we did the executor. I can't remember if we did the completion service version. Okay, so remember, we've got a parent with 3 streams going in, the standard in and the output stream of 2 children that are filtering standard in. So standard in goes through into three different processes, which usually means that each process gets its own turn. So the lines you type of the keyboard alternate between going here, going through here, and going through here. Okay, and then the idea is what goes inside the parent. How does the parent read from these 3? So we want to read in parallel. Okay, so originally we read in serial. That's this program here. Create 2 pipe children would read from the 3 streams just in serial. Read until end of file on one of them, then read till end of file on another, then read till end of file on the other. Okay, that was one version. And then we did it with threads. So there'd be 3 threads in the parent. One thread was just reading this one thread was reading this one, and one thread was reading that one, which works fine. Okay, but if you replace these 3 streams with files, then 3 threads isn't load balanced well. Because if you have 2 big files and 1 small file, then the thread that's reading the small file on one core won't have anything to do when there's 2 threads reading big files on these cores. It doesn't chop the files up into pieces in any way. So having 3 threads is good parallelism, but it's not good load balancing. Okay, so same thing with what we saw with the fork join stuff. You need to chop problems up into little pieces to be able to load balance them. Okay, so in the case of this simplistic example, it really didn't matter if we have 3 threads or not, because these are just reading character IO. But we're really trying to prepare for when this is going to be reading one file, this one's going to be reading another file, and this one's going to be reading another file. So we really want to set it up so that we can divide the work among the 3, divide the work somehow. Okay, so the first attempt at dividing up the work was using futures. Okay, we set it up so that the future, we set it up so that a future was a thread that read one line. A future was a thread that read one line from one of those inputs. Okay, so a future would just read one line from this input. Another future would read one line from this input. Another future would read one line from this input. That's an attempt at cutting the work down into smaller pieces. Okay, so you know, you create three futures, one for here, one for here, one for here. And as soon as a future is read a line and processed it, you can create another future for this thing. And when this future is read a line and processed, you can create another future for this one. Okay, so if there were three files here instead of just three streams, if there were three files here, when one file was done, you would still have three futures that could be, there'll be two files here, but there could still be three futures grabbing lines from each of these two files. Okay, that would be what we want to have happen, is that when it becomes a matter of there being three files here, if one of the files is emptied and there's still two files left, the fact that we have three futures means that the futures could be grabbing files, grabbing lines from each of these, from these three futures could be grabbing lines from two streams. Okay, so that was the future idea. It started breaking the work up into smaller pieces. Now the work is read one line, that's this part here, and then filter the line. You know, we filtered the line by echoing the vowels. Okay, remember we just did some trick where we just repeat vowels. So it's just something to pretend to be filtering the text. So we were just echoing the vowels. So, but notice that the work of a future is really two things: read some input and do some work on the input. Eventually, we'll break that up into two units, because there'll be an advantage to breaking that up into two pieces of work instead of being one piece of work. Okay, all right. So then the future created one piece of work for every line here, here, and here. Okay, but we were polling the futures. You know, how do we know when a future was done? Well, we had a loop. We have a loop that polls as long as there's three streams, so we're looking for three end of files. We're done when we get three end of files. We just keep looping, and the loop just keeps asking, it goes to this future and asks, is it done? If the future is not done, then it goes to this future and asks, is it done? If the future is not done, it goes to this future and asks if it is done. If none of the three futures are done, it loops and asks them again. So this is polling, okay? Polling is inefficient of CPU utilization. If you're in here, you can hear that when I run this program, my fans all turn on in the computer, because the CPUs are actually busy, not really doing much work. One core is busy doing the polling. In between the I/O operations, there's really not much to happen, but this thing is still polling. So, when you read one, if you think about what would happen, you would read one line from this input stream and start working on it. Read one line from this input stream, work on it. Read one line from this input stream and work on it. So the three futures would be busy, and you have to wait for one of them to finish. But in the meantime, one CPU is polling them just super fast. Are you done? 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 Okay, so that's inefficient. There's one thread polling these threads, asking when they're done. Okay, so we don't want to waste CPU cycles on polling. Okay, so then we go to another way to do this. Okay, we throw the futures into an executor. Okay, we throw the futures into an executor. Okay, oh, that's this one here. Okay, so now this one still does polling. It actually isn't going to be done with the polling yet. We get rid of the polling when we go to the thing we call the completion service. So we throw the threads into an executor. There was another thing wrong with the executor version, the future version. Okay, let's go back to the future version. There's two things wrong with it. Besides the polling, besides the fact that it's polling, it's actually creating a thread for every work unit. Okay, every work unit creates its own thread to run the work unit. So every future carries his own thread with them. You would rarely do this in most programming situations, but it's something you can do. each future is its own work thread, okay? But that meant that if we were reading 3 files and each file had thousands of lines, we'd be creating thousands of threads. And we saw in the fork join case that that overwhelms the operating system. Operating systems do not really like it when you tell them to create thousands of threads. Hundreds of threads they can do pretty much, but thousands of threads really get to be too much. And in fact, this could be tens of thousands of threads. If you're reading 3 files of a gigabyte each, there could be tens of thousands or hundreds of thousands of lines of code in the 3 files. So you're potentially creating massive numbers of threads here. So there's 2 problems here. One is the polling problem, and the other is the fact that you're creating way too many threads. So the executor is the one that takes care of the thread problem, okay? So the executor creates a thread pool. We create an executor thread pool with 3 threads in it, okay? And then our futures now don't do their own work. The futures just represent some work, but they're going to be given to the executor to do. So the executor holds the threads, and then each one of these threads is going to eventually do thousands of work jobs for us. Okay, so the thread pool, I've mentioned this many times. It's a confusing way of calling it. It should probably have been better off called a thread work pool or a work pool. The pool is actually the work that needs to be done. There's 3 fixed threads, but we're going to dump lots of work into the executor, and the 3 threads just keep grabbing work out of the pool and doing the work individually. So the pool is a work queue and 3 threads. Okay, so our pool is a work queue and 3 threads, and we're going to put 3 futures in it. Okay, and what's going to happen is we're going to create 3 futures that do, each future is going to do a task. The task is the same as it was before. Read 1 line and filter it. But now the task doesn't carry its own thread. The task, if you go down here, the task is the same code, except it's not in a thread anymore. The task just is a function called call. Okay, it's instead of being a runnable function in a thread, it's just a callable function sitting by itself. So somebody has to do this work. It doesn't carry its own thread with it. So we'll create 3 futures wrapped around these 3 tasks and give them to the executor to do. Okay? All right. And then we'll poll the executor to ask it, well, we're going to poll the futures just like before, but there's only 3 of them now. And we're essentially, when we're going to poll the futures to ask them when they've come out of when the thread pool's done with them. So we give them to the thread pool. The thread pool does them, but we keep a reference to each future so that we can poll the futures. Are you done yet? Are you done yet? Are you done yet? So we're still polling. There's only 3 threads, not thousands of threads, but we're still asking each thread, are you done yet? Are you done yet? When a thread is done, we get its job and replace it in the thread pool with a new future. So each time a future completes, we replace him in the thread pool with a new future, put the new future back in the thread pool. We use the same reference. So we're going to reuse the reference to the futures are new, but we're using the same reference. Okay, so each time we create a new future, and put them in the thread pool, but we keep using the same name for the 3 futures. So we have 3 names for constantly changing futures in the thread pool. Okay, but we're polling. Okay, so yeah, from the point of view of this picture, there's a future to read 1 line from here, a future to read 1 line from here, and a future to read 1 line from here. They're each in the thread pool, and then we're polling the futures, asking, are you done? Are you done? Are you done? As soon as the future is done, which is read a line, we replace it with another future, toss it in the thread pool, and and then poll the future to see when it gets done. Okay, so When a future is done, okay, we check its result. If it's null, that means we hit end of file. Okay, so if the result from the future is null, we hit end of file. So if the result from the future is not null, we get the line, we print it. See, we get the line and print it because that's the line that's been read and filtered, and then build a new future out of a task, build a future out of the task and put the future into the thread pool, and then loop around and ask, are you done? Are you done? Are you done? And just see whichever one gets done next is the one that'll be replaced in the thread pool. Okay, so now we've got a fixed number of threads. Notice we're incrementally solving problems. We first solved the problem of breaking the workload into little chunks, because when we use 3 threads, using threads like this, 1 thread for this stream, 1 thread for this stream, and 1 thread for this stream, we had efficient use of threads, but not good load balancing. 1 thread had to read this file, 1 thread had to read this file, 1 thread had to read this file. When this file was done, that thread couldn't go help these 2. Okay, so we break the work up into tasks. That solves the load balancing problem. Okay, when we break the work up into tasks, we're using futures. We need to know when each little task is done, but that introduces a polling problem. Okay, well, first we break the tasks up into futures where each thread does a task, and that's actually kind of an intermediate step that's not a very good idea, that just have a task for each future. Okay, so then we go to the executor case. Now we're back to 3 threads. Okay, so now we got 3 threads with good load balancing. So if we skip from the threaded version to the executor version, we've solved the problem of keeping us down to just 3 threads, because there's only 3 streams, so we should have 3 threads. And actually, the number of threads should be the number of cores. So I just used 3 here because it was a pain to keep creating more of these things here. But I have 12 cores in the machine. I could have gone up to 12 of these, okay, and then have one thread for each of these streams. Okay, so I could have gone up to 12. Okay, so I've got 1 thread for each stream, so that's efficient. I'm not creating unnecessary threads, but because I'm using futures and I don't know when they're done until I ask them, I have to create a poll. I have to keep asking threads, are you done? Are you done? Are you done? Okay. So then we switch to a more sophisticated kind of polling, a more sophisticated thread pool. A thread pool that's called a completion service. Okay. So this one's now going to get rid of the polling issue. What a completion service does is it wraps something called a completion service around a thread pool. So now we've got a completion service wrapped around a thread pool. So here when we create a completion service. Okay, here we create the thread pool. Then we create this completion service wrapped around the thread pool. What a completion service does for us is it efficiently does the polling. You know, it hides the polling from us. Instead of us having to sit there and ask, are you done? Are you done? Are you done? The completion service is going to tell us when a future is completed, okay? And it'll let us block. And essentially, we're going to see what we're going to do is, instead of a while loop that does polling, our while loop will call on the completion service this thing called take. What take does is it waits for a task to complete. Now, how the completion service knows how the task is done is up to them. That's done internally in the library. They probably don't use polling, because if they use polling, they'd be back to what we were doing, which was inefficient. So they probably have some mechanism for creating a system where they can keep track of the threads in the thread pool for us, find out exactly when one of the tasks in the thread pool is completed, and let us know exactly when it's completed. I don't even really know how that's done internally in the completion service. I haven't had time to figure out, if we wanted to write if you wanted to write your own completion service, like is there an easy way to do it? I'm not really sure. Maybe there is. I don't really know. But the completion service, I mean, we can imagine it's doing polling, but it's probably not, because then there would be no reason to have this service. Because when you run this, it doesn't waste CPU cycles. You know, when you do this, you don't hear the fans immediately kick on my computer when you run the completion service one, because when we ran this one, this polling was occupying one whole CPU. One whole CPU on one whole core of the computer was doing the polling, because you just keep asking, are you done? Are you done? Are you done? And if all three of them aren't done, you just immediately ask them again, are you done? That way you can find out exactly when the first one of them is done. You could mitigate this polling by doing, are you done? Are you done? Are you done? Sleep for 10 milliseconds. And some people do it that way. They put a little sleep in their polling loop. But then you're always off by, say, 10 milliseconds. You can never respond to a task in less than 10 milliseconds. Because if a task is not ready, you sleep for 10 milliseconds. Okay, and sleeping, that does cut down on a lot of the CPU work, but in a really high efficiency server environment, making your polling loop dead for 10 milliseconds at a time is probably not acceptable. Okay, so you really don't want this guy being asleep for 10 milliseconds at a time. So you could mitigate the polling by asking each future, are you done? If the three of them are not done, then you sleep for 10 milliseconds, then wake up and ask them again. But that really actually kills your performance, because you can never, your response time now is at best every 10 milliseconds. Okay. Now the executor is going to be smarter than the completion service is going to be. It's supposed to be smarter than that. The completion service is not going to do continuous polling, but it's still going to give you really good response time. I hope. I haven't really tested it, but it could also it could be that the completion service does put itself to sleep for a few milliseconds. So I kind of doubt that it does that too. My guess is the completion service uses lower level threading tools to figure out a way to find out exactly when something is ready in the thread pool. And then we block on take, and we're assuming that the instant one of our futures becomes available, this thing will return for us. So we're blocked on take, okay? And we're not being able to do we're blocked, so we're not able to do anything else. But this is, if this is our server, we really don't have anything for our server to do until it responds to the very next. We want our server to respond to the next job as quickly as possible. Okay, so being blocked when this guy doesn't have anything to wait for is okay. When he's waiting for something, that's okay, because the other threads are busy doing work. When this guy's blocked, there are 3 threads doing work for us. And really what he wants to do, he's the scheduler in a sense. He just wants to know, when is one of these 3 done? The instant one of these 3 is done, he wants to know which one it is and then replace them. So when one of the futures is done, the completion service gives us a reference to the completed future. So what we do is we go and check, we're comparing references here. Is the future that just popped out of the completion, out of the work pool, the thread pool, is the future that just popped out of the thread pool our future 0? If it is, that's the one we want to replace. On the other hand, the future that popped out might be our future 1. Remember, our future 0, 1, and 2 are from here. We created them. This is just like before. We're going to keep reusing these references to the futures that we put into the work pool. So when something pops out of the work pool, the object that pops out is going to either be, it's going to be what this one's pointing at. This thing points at the object we put into the work queue, and then we have a reference to it when it pops out. Okay, so we're keeping a copy of a reference to the object, so that when something pops out of the work queue, we can ask, is the one that popped out this one? Or is the one that popped out this one? A lot of times you don't care which one it is. In our case, we want to know if it's child 1, child 2, or the parent. So we have kind of a quirky thing here where we're not treating these streams as equals. we're doing something different on this stream, something different on this stream, and something different on this stream. So we have the kind of an odd situation here where we're not treating all the work as uniform, as homogeneous. In a lot of situations, there would be no difference between the work coming out of these, all these streams would be essentially the same kind of work. But in our case, we want to know whether what popped out of the work queue is it child 1, is it child 2, or is it the parent child? Okay, actually, I think the order was this is the parent thread, this is the child 1 thread stream, and this is the child 2 stream. Okay.
This is almost identical to select.
Yes. Yeah. That's a good point. Yeah, we're essentially mimicking select here. Yeah, we get something out of the work queue, and it's kind of like a thing, and we check what's in that guy, and we check which one. Now, select can give you multiple answers. This can only give you one. When select returns, it could say there's 3 things ready at once. Select could, if this was really select, we could be finding out that 0 and 4 are both ready at the same time. In this scheme, if 0 and 4 are both ready at the same time, only one of them pops out of the work queue, and then we'll take care of it, and then the other one will pop out of the work queue immediately afterwards. So unlike select, this one can't return to us a couple jobs that finished at the same time. Okay, so it's very close to being like select, but it only would let us know that one job, if 2 jobs completed at the same time, one of them is going to get handled first. One of them will pop out of take. One of them will pop out of take first, and then the other one will. Then when we loop around, the other one will pop out. Okay, so we can't get 2 references out of take at once. Okay, all right. So we are no longer polling. We're letting the polling work be done by the completion service of the Java library, and we're assuming, the completion service, and we're assuming that the completion service is written real efficiently. That the completion service does its polling in a very efficient way. So it's not, so 2 things. It's not wasting CPU cycles doing polling, but it's also not doing something dumb like poll the futures, then sleep for a little while, then poll the futures again, then sleep for a little while. We really hope that that's not what they're doing inside of their completion service. We hope that they are very efficiently letting us know exactly when one of the futures is completed. Okay? All right. Now, we're still, if we were to turn this over to files, we would have a very efficient way of breaking the files, like this is a file, this is a file, this is a file. We're reading one line from that file, one line from that file, one line from that file, and processing it. Okay? But there's something kind of wrong here. When we read a line from that file, we can't read another line from that file until we process the line. We set it up so that if we go look at a task, the task reads the line, that part blocks. Okay, actually, see, it blocks until the line is ready. Then when the line is ready, we read it. Then this code here is processing it.
Oh,
Okay.
well, the way that you solve that is just don't use scanner. Use a class that will buffer your input for you.
No. We want to break the reading from the processing. Okay. We want to break the reading from the processing. We want to, this thing's got a block. You can't have a line until a line is ready. Okay. So the first step is you have to block until the line is ready. And then as soon as the line is ready, you just read it. Now, this is not going to block. There's nothing, we don't need this thing to be buffered. When this thing unblocks, this thing gets the line immediately. Okay. All right. But see, now at this point, we could read the next line. But we can't read the next line because we have to process this. What we would like to do is hand this work over to another thread, while this thread would be allowed to block on the next line, immediately queue up another IO request. See, right now what we're going to do is we complete an IO request, and then instead of immediately queuing up another IO request, we spend some time doing a little bit of work here. What would be better is as soon as that IO request is completed, we would say, oh, here's some work to put in another thread pool. This work should be sent to another thread pool. And then this guy should immediately just say, okay, now I can go read the next line. So what we're going to do is the next step is to break this problem up into a pipeline of 2 thread pools. One thread pool that's going to have the job of only reading lines and only doing IO. As soon as it's read a line, it'll build a little job to process that line, stick it in a thread pool, and then immediately go read the next line. So the next one is this one called pipeline. Okay, what it is, it's now going to use 2 thread pools. One of them is going to be the completion service thread pool. That's going to be doing the IO. Okay, so there's the completion service thread pool, just like before. It's going to be doing the IO. Okay, but then we also have another thread pool that it's going to be. Oh, I'm sorry. This is the completion service thread pool that does the IO. So it's pool 1, and then the completion service is wrapped around pool 1. Okay, but the jobs we put into this thread pool only do IO. The job will, and let me show you down here. If I go down here and I look at a task 1 job, it just says block until the IO is there. As soon as the IO is there, read it and then quit. That's it. The future just waits for there to be a line. As soon as the line is available, it reads it, and then the future returns. If this thing returns null, then we set the result to null because we hit end of file. So if this thing returns with a null, or I'm sorry, if this thing returns false, we've hit end of file. If it returns true, read the line. Okay, so these are tasks that do nothing but read lines. The rest of the work is going to be in another thing called a task 2. These will be put in a different thread pool. These do the filtering. They take the line that came out of task 1, and they'll do the filtering of it. They'll do the count. So this is the computable part of a task, and this is the IO part of the task. We're breaking the task into an IO part. Task 1 is the IO part. Task 2 is the computational part. Okay, and we're going to have separate thread pools for them. Okay, we'll run this, and we'll see how it's kind of neat when we run this. See how it works. Okay? We build the thread pool that does the IO with a completion service wrapped around it. Okay. We build a thread pool that does the computation. We don't need a completion service for this, because when task 2 is finished doing its filtering, we don't need to wait for it. We can just let it print out its output. Okay. So when this task has finished doing its work, it'll just print its output to standard out. We don't need to know when that finishes. We need to know when a task 1 is done, because we need to use the result of a task 1 to create a task 2. But we don't actually need to know when a task 2 is done. We throw it in its thread pool and we don't care. Once we've thrown it in its thread pool, when it's done, it'll print its output out, and we don't need to be told that task 2 has been completed. So we need a completion service for the IO operations, but we don't need a completion service for the compute operations. Okay, so 2 thread pools, pool 1 and pool 2. Pool 1 is wrapped inside of a completion service, and pool 2 is just going to be used as a plain old executor pool. Okay, we create IO tasks, 3 of them, to get started. We create futures. We submit the 3 IO tasks, and we get back a future to wait on. Each one of these futures tells us that an IO operation is completed. So now we go down here. The code kind of looks the same for a while. Ask the completion service to give us a future that's done. We check which future is done. Okay, if it's future 0, we check if it's null. If it's null, that we're done with that stream. Okay, if the future is not null, we build a task 2, we build a task 2 task out of the result from that future. The future gives us the line it read, and we say, okay, filter that line. Okay, so future 0 get gives us the line that we just read, and here we say, now build the filtering task and put it in the thread pool, the second thread pool. And then build a new task 1 task using scanner 0 to read the next line. Okay, so there's a little pipeline. Okay, you're going to read from the scanner, then the output of the scanner is going to get put in task 1, and then you read from the, then you create another task that's going to read from the scanner, and the result of that scanner is going to be put into another task. Okay, so there's like a little 2-stage pipeline. Task 1 is the first stage in the pipeline. The output of task 1 goes into task 2, then we start a new pipeline. We start a new little pipeline there. Okay, now let me run this. Now it runs just like the other ones did. Okay, if you run it, okay, okay, that was when I typed that A. That was standard in going into child 1. Child 1 is the one that makes child 1 makes things uppercase. Makes vowels. Child 1 and child 2, which are weird echoes, they change the case of vowels. So lowercase turn to uppercase and uppercase turn to lowercase. Then stream 3 is the one that duplicates vowels. Stream 4 triples vowels, and stream 0 quadruples vowels. Okay, so right now, one of the futures completed. It was the future from this stream here. Okay, then if I type an E, that one went into this, that one went through here. Okay, it got uppercased by child 2, then it went into here and got tripled. Now, because we got this standard in going into 3 streams, the next one, if you do I, see it got quadrupled, but it didn't get its case changed because that one went through here. So there's no weird echo in the stream. So the letter I just went into here, and then stream 0 has the task to quadruple vowels. Okay, and then A, I'm back to stream 3. Well, in this picture, I'm back to stream 3, and then O back to stream 2, and U back to stream 0. Okay, now if I type some control Z's, like now I know I'm on this stream here. Okay, I'm back to this stream here because they just they cycle through them. If I type control Z, I get child 1 ended. Okay, that was child 1 stream ended. Control Z is going to give me child 2 stream is closed. So now only this stream is left open, and I can now all my vowels will be quadrupled, and letters that aren't vowels just get echoed. Okay. Okay. And then if I type control Z now, that closes the last stream. Okay. Now I print some information about the thread pools here. Okay. If you can print out statistics from the thread pools. Okay. This is the thread pool that was doing the I/O operations. This is the thread pool that was doing the compute operations. Notice that one of them did 14 operations and one did 11 operations. Okay. And if you go through here, you'll see that there was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, did I miscount something? There should have been 14 inputs. Yeah, 14. The control Z is the 14th input. Now, but why are there only 11 compute tasks? Why were only 11 jobs put in the compute pool?
Control Z?
Yeah, the control Z's didn't do what?
They didn't
do anything.
Yeah, well, they didn't produce.
Other than shut down a stream.
Right, they didn't produce a worker. They didn't produce a task in the there was no filtering to do. So each control Z represented an I/O task, but it didn't represent a filtering task. So there were 3 less filtering tasks put into the the other work queue. Okay.
So,
Mhm.
I'm not exactly sure if this will scale to disk I/O all that well.
Well, I'm hoping it will. We're gonna find out probably by Wednesday. Yeah.
I think more than likely it will be actually substantially slower.
I don't think so. I think it'll scale, but we have to worry about well, I'm going to show you some stuff we have to worry about. We have to worry a lot about buffering. We have to worry a lot about buffering. Why
I
would you
think if
it'd be
you're
slow?
reading, I think if you're reading off of an SSD, you won't see any real penalties. But if you're reading off of a single spinning disk, you should see large penalties on small files because the read head has to move around the disk, and while it's
But it's
moving,
got to do that no matter.
it's not reading.
But it's got to do that anyway. It doesn't matter
But
if
it's
you're
going to it's going to try to fulfill all of your different read operations by interleaving them,
well,
and
that's
that's going to cause head seeks.
not if you have not if you bought a good hard drive. Good hard drives, when you're given a whole bunch of requests, they reorder the requests into an optimal strategy. A good hard drive will take all the requests it gets and say, which order should I do these in? Not first come, first serve. First come, first serve is a really bad strategy. It'll say, well, let's see, request 1 and request 10 are on the same track, so let me do 1 and 10. Then the next track over was request 17. So a good hard drive does efficient scheduling. So, but see, that problem would appear no matter how you were doing your I/O. Like, like if you had to do a bunch of files, what else would you do? If you have to read from 10,000 files, you don't want to read it from file 1, then read from file 2, then read from file. Well, you could. You're comparing that to reading everything from file 1, then reading everything from file 2, right? But see,
Yes,
file 1 and
I
file
think
2
that's
are
going to
highly
be.
Think about it. That's not. There's no reason to think that's a better strategy. Okay, suppose I have 10 files. File 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Suppose file 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 are all highly fragmented. So that means each file is all over the hard drive. Then reading all of file 1 is in no way more efficient than reading all of the files at the same time, because their sectors are just randomly all over the platter. Now, if you had defragged your hard drive before you ran your experiment, and you actually had file 1 defragmented and file 2 defragmented, then you can make the case that it might be faster just to read all of file 1, then read all file 2, then read all file 3. But you would have to know that you defragmented all those files. Now, in real life, you can't defragment a hard drive before you do an experiment. So you have to assume that the sectors of each file are randomly distributed over the hard drive. That's pretty much the case with most. That's what you should assume. But then it's no worse to read 10 files interleaved than to read 1 file, because they're just randomly distributed.
All right, that sounds right.
Yeah, but now that does assume that you're highly fragmented. Okay, if you did have a way, and there might be, like for example, a database server might make an effort overnight to defragment the database.
Well, as far as I know, Windows routinely does like automatic defragmentations, like weekly or daily by
No, as
default.
far as I know, it never defragments unless you ask it to.
No, I actually checked this recently.
Okay,
Windows by default these days does that.
Wow, I have to check into that, because it used to be that Windows
Yeah,
never
it used to be that
defragmented.
it wouldn't do it. You have to go tell it to.
Yeah, and you had to reboot your computer to do it. You had to run a special software and everything. Yeah, that might be it. Maybe it does. Yeah, but you can't. But see, even then, suppose
Even
you're
then, you
running,
can't guarantee that they're not.
Yeah, after your server's
fragmented.
been running for 27 hours in a row, the hard drive's probably fragmented itself. And to defrag it, you'd have to shut the server down, defrag the hard drive, and bring the server back up. Now, that can be done with a database. Like a database server might do that overnight. Okay, but in this case, we're going to assume that there's no reason to think that the data files are contiguous on the hard drive. So any one data file is going to be splattered all over the hard drive, and so it doesn't matter if we're reading one file or 1,000 files. we're essentially reading sectors randomly distributed over. But in fact, the more files we give it, the more likelihood that the head drive scheduler can find an optimal strategy.
All right,
The
that
more-
makes sense.
The more you give it to do, the more likely it is it can find a really efficient path through the hard drive to read. Instead of going from one end of the hard drive to the other end of the hard drive, back to the other end of the hard drive, it might be able to find an effective strategy. Okay, all right. So now let's play another little game with this example here. Okay, to show you that I've really separated the I/O operations from the compute operations. We play a game of sleeping. Okay, put us. Uncomment this line. What this does is let you know when the read operation is done. Notice that when the read is done, I go ahead and print it out, okay? Just to see that it's done. So this way we'll have feedback that lets us know when an I/O operation is completed. Then go down here and uncomment this line. This pretends that the compute operations are real long operations, okay? So this has the effect of making compute operations appear to be long-running operations, okay? Now, in the previous version, if you did that in, I didn't put that in this code here, but actually we can do it. What we just did was, if you think about, this is the previous version. As soon as you read a file, you print it so that you know when it's read. But then you pretend that the that the filtering operation is very long running. So you create the impression here that the I/O operation, the compute operation is very long running. So make it 5 seconds. Okay. Now, what happens if I do that in this? This is the case where everything is combined. Okay. So let me compile that and run it and just see what happens. Okay. Here is an A, and it's echoed. Okay. I don't know why it echoed no. Okay. There. See how it took a long time to get the output. Okay. And then here's a U. What did I do? Let's see. Well, why did it echo no? What did I do wrong here? I probably when I copied it.
Result starts as null, doesn't it?
Yeah. Let's see. Copy and paste doesn't always work. So oh, I'm supposed to print one line. Yeah, because of so I should have printed one line there. Yeah, print one line. Okay. Run it. Okay. A. Well, okay. 5 seconds and the job is done. Okay. Now, and then here's E. Okay. 5 seconds takes it for the job to get done. Okay. Now, what's the result of this? If I do AEI real fast, I can't do any other work now. See how they come? Yeah. And what now is okay. Notice how the work. Notice the work's coming out every 5 seconds. Okay. Okay. Now, when every 5 seconds I read something from input and echo it back out, and then I read something from the input and echo it back out, and what it is now is that these things are, these guys are coupled together. Okay. You can't read another thing on this input until this work has been done. So even though the file is ready to be read again, you can't read from the file again until all this stuff happens. Okay, so it's because as soon as you've read one line from the file, you could just read a second line from the file. But we're not allowed to read a second line from the file because we've got this long wait here while this slow work happens. Okay, and what happens we see that is that the it you know it echoes right away. It echoes right away, but then it takes a long time before it finishes the output, and then it can go read the next input. Okay, right, now let's see what happens in the other version. This one's going to behave a little bit differently because in this one, the two tasks are separate from each other. This one does I/O, and it's separate from this one doing compute. Okay, so okay, now I have to wait 5 seconds to get the actual compute. Okay. Okay, so it takes 5 seconds to wait for the actual computes, but now do a bunch of input real fast. Okay, notice that they echo. See, now it's only the computes that I'm waiting on. If you notice that all the echoing, the I/O is done right away. The I/O happened. All the I/O happened immediately. There was no delay in any of the I/O. All the work came out here. Oh, I closed that other window, didn't I? Oh, that was kind of dumb. Okay. You have to like compare the two windows to see how the ordering is. Okay. Do a bunch of input real fast. Okay. Now see the pause there where nothing's happening? Then there's some echoing and some computing and some echoing and some computing. Well, it's not really even reading until it, see, and that output is very different than this output, and it's actually an important difference. In here, all the reading happened right there. All my typing in was processed immediately, and then all I ended up doing was waiting for the results to come back out. But there was nothing stopping my input output. My input output happened right here. Okay, and you can see that because A got echoed, E got echoed, I got echoed, A got echoed, E got echoed. Whereas here, where is it? No, that's, oh, you have to be real careful to parse this. Because see here, this is echoing that O there. Okay, and this is echoing an A from up there. So this one got echoed, and this one got echoed, and this one got echoed at first, but then these didn't get echoed until down here. See? So yeah, I should have used different letters, but you can see that like this O here, I think, is this one down here. You have to kind of trace through them. But see here, everything got echoed right away. E, E, I, A, E, E, I, A, E, E, I. Then down here, there's no echoing. This is just outputs. These are the final results of the filtering. And here there was a delay from I typed an input, but there was no response to that input for a while. Now, another way to think about it is if these were clients, if this was a server, what happened over here was, you can think of it in this picture over here. A client came in and their data was read. And then work was starting to be done on that client. While the work is being done on that client, no other client can appear on this line. If another client comes here, he's just told, wait until I'm done processing this client here. Okay, so this line, this input stream can process one client, and it can't even get the data from a second client until it's computed all the results of the first client. In this one, same. The way you should think about it is that this stream can read input from a client. As soon as it's read the input from the client, it gives the work to somebody else and then turns around and says, okay, next, in response to the next client immediately. So this is like a checkout lane where there's two workers here. One worker gets the work from customers and gives it off to somebody, and then immediately is there ready to take work from the next customer. In this version here, there's really only one worker there. So that worker gets work from a customer and goes over here and does the work. Meanwhile, another customer is just standing there waiting while this work is being done before this customer can give his work in. And that delay between when the customer showed up and the customer could actually give their work to a worker was this echoing delay, where over here, this O was entered in here, but it wasn't echoed till down here. See, there's the first O, there's the first O being echoed. And that delay was a customer showed up and the server made them cool their heels while the server was doing work until the server could come back and get their request. Over here, every customer gets handled immediately. As soon as this customer shows up, you get their work. As soon as this customer shows up, you get their work. Now, they don't get their result back for a while, but at least the customer is essentially told, you think of it as the customer came up to the window, handed their work over, and got a ticket saying your work is being worked on. As opposed to in this one, the customer comes up, hands over their work, and just waits, they're given a ticket that when their work is done, but then the worker goes away and does the work. If another customer comes up to the window, they're just sitting there waiting for the worker to come back. Then that worker gets a ticket, they hand over their work, and they get a ticket. In the better version, each customer shows up, hands over their work, and gets a ticket. As soon as they get a ticket, another worker can walk up and hand over their work and get a ticket. Then another worker can walk up, hand over their work, and then the workers, the customers can just show up one after the other. This is called very responsive. This system here is very responsive. Because we partitioned the I/O from the filtering, this one is very responsive. As soon as a customer shows up, we get their work and give them a ticket. Get their work and give them a ticket. Now, their work isn't done till down here. That's the same as in this other one. The work actually isn't going to get done till 5 seconds later. We can't change that fact. The latency of doing the work is still 5 seconds in both of these cases. So the latency in both cases is 5 seconds, but this one's got a response time essentially of 0. This one's got a response time of 5 seconds, a latency of 5 seconds, and a response time of 5 seconds. When a person shows up, they have to wait 5 seconds, like this O showed up. O showed up, he waited 5 seconds before he can even give his work over to the work queue. So he had a 5-second response time, then a 5-second latency. Over here, he has an instantaneous response time. When an A shows up, the A, he's immediately given his ticket, his work is accepted and he's given his ticket, and then he's got a 5-second latency till his work is done. So he's got a 0 response time, 5-second latency. Over here, you have 5-second response time and 5-second latency. Okay, so we've really improved things by putting this delay in here. Now you should run these yourself and convince yourself that there really is an improvement over here than over here. Okay, you really have to see that this is an improvement, and think of it in terms of this being a server and how it's serving customers. You really don't want to get to the front of the line, give someone your job, and then have them walk away and start working on the job. It doesn't bother you so much, but it bothers the person behind you, because when the person behind you comes up here, there's nobody here to take their work. Okay. Whereas over in the better system, there's 2 workers for every thread. One worker is just accepting the jobs, and the other worker is doing the work. So that's the little pipeline. That's this pipeline here. Or if you want to think of it, that's the pipeline right here. That's the pipeline right here. Okay. You get the work from the worker who's standing at the window. The worker who's standing at the window gets the work and feeds it immediately to this task 2. And then we create a new, now we're actually creating new workers each time, but you immediately put another worker at the window. So there's immediately another worker at the window that can wait for the next customer. And then when that worker gets a work from a customer, it passes the work off to another worker who goes off and does the work. Okay. All right. So we've split. This should be both responsive and fast. I'm hoping this will be responsive and fast. Okay. If this is file 1, file 2, file 3, what we have now is hopefully a system that could very quickly read all the lines from this file, all the lines from this file, all the lines from this file. And in fact, if this is a short file, and this file is, well, eventually we'll rewrite it so that the idea would be if this is a short file, there's 3 tasks over here. One task could actually start alternating on, say, one task could help these 2 tasks here. When somebody, even in the brief period of time it takes them to read one line from here, somebody else could go in and read a second line. Okay, we'll see. But we very quickly can read lines. We essentially can read the lines as quickly as possible from here, and then we have separate worker threads that actually do the calculation. What we'll see when we want to do this with files, like right now, we have 3 threads for each work pool. That won't be the right strategy when we do switch to files. Okay. Work pool 2 does the computations. It should be, well, the number of threads here should be the number of cores we have. Okay. But this should be a fairly large number. Okay. Suppose we want to read from 1,000 files. You can imagine this being 50 or 60 threads, so that we would have 50 or 60 threads being able to cycle through files and be ready to read a line from each file. Really, it boils down to how many I/O operations can our hard drive sustain at once. And that takes real experimentation to find out. The thread pool that will be handling I/O really should be a number of threads that somehow represents the maximum number of I/O operations we can kind of have going on the hard drive at once. How many I/O operations is it reasonable to throw at the hard drive at one time? That's what we were talking about earlier. With how good a head scheduling algorithm there is there. You don't want to give too many jobs to the hard drive at once. It may just start screwing up the hard drive. But there'll be some number that would be a good number. It's not going to be 3 or 4. I actually don't know. It might be in the dozens. I'm not really sure with modern hard drives how many I/O operations you can throw at a hard drive at once. Okay, so you can have all these I/O operations in flight at once. Okay, so this thread pool can have a whole bunch of I/O operations in flight at once, but this thread pool should still only be as many cores as there are. Okay, because there's no point having more threads than there are cores for compute-bound processes, because you cannot share cores with compute-bound processes. These threads will be mostly blocked. See, suppose there's 50 threads in this pool. There won't be 50 running threads. What that'll mean is we could have 50 I/O operations in flight at once, but those 50 I/O operations are going to all be blocked from the point of view of the operating system while the hard drive is doing them, while the hard drive is queuing them up and executing the hard drive motions to do the I/O operations. Maybe 50 is too many. I'm not sure. I don't really know what that number should be. Like,
it depends on the hard drive.
Right, it's going to depend on.
Low-end hardware will choke on just Windows alone at idle, believe it or not. Higher-end stuff can handle dozens.
Yeah, so maybe this might be in the dozens. If it's a solid-state drive, it might even be completely different.
Solid-state drive will just handle. It doesn't matter.
It may not. Yeah.
Throw stuff into its queue all day long. It does not care.
And then in a server environment, you could have 20 hard drives attached to the server in what's called a RAID configuration. So the hard drives you have these sophisticated hard drive systems where work is doled out to the hard drives by the RAID system. So you could imagine that even if you had spinning hard drives, you could still make this number quite large on a server if you have like 20 hard drives connected to the server in a RAID environment. Okay, so it would be a lot of experimenting to figure out what that number would be. This number is clear. This is the pool doing the compute-bound operations. This number should be the number of cores you have, because you can't. Actually, it's a bad thing to have. Suppose I had 8 cores and I made this 16. Then I'd be trying to schedule 2 threads on each core. That means that'll work. I'll have 2 threads in each core, but then I have to context switch between the 2 threads in each core. So now I'm wasting time context switching. Why waste any precious CPU cycles on something you don't need to be doing? Instead of having 16 threads on 8 cores and having 2 threads per core and context switching, just put 6 threads on 6 cores. Each core will run 1 thread to completion, and then it'll go grab another job, and then it'll run that job to completion. Since these are compute-bound tasks, they'll never block. So as soon as you throw one of these guys on a core, just let the core finish it. So don't put 2 of these on 1 core and make the core context switch between them. That's just wasted CPU cycles. Put one of these guys on a core and wait till the core completes it. Then let the core grab another job out of the work queue and run that task to completion. The key is that these don't block. That's real important, that we've pulled the I/O out of this job. This is a totally compute-bound job. If this job actually did a little bit of I/O, well, actually it does do a little bit of I/O. I made it do some print line here. I was kind of cheating here. I made it do a print here. Okay. So, I mean, in a way, I probably shouldn't have. I should have probably had that print line in another task. So I could have created a 3-stage pipeline: 1 stage read, 1 stage computed, 1 stage printed. And that may actually even, in the long run, that may actually speed things up a little bit to have 1 stage read, 1 stage pure compute, and then another stage that can do all the little I/Os to do the outputs. Okay, so that probably would speed things up, because now this is going to. Well, the thing is, print doesn't block anyway. So the advantage here is that this doesn't block. You call print, your I/O is sent to the console window, and then you return immediately. It's up to the console window to do the I/O when it's ready to. So
You would just be rewriting the print routine anyway.
Yeah. So this doesn't. I don't think this one actually matters because it's not a blocking I/O operation. Unlike the read, which blocked until there was data ready. You had to, if it's from the console, you have to block until somebody types something. If it was from if it was reading a line from a hard drive, if this was reading a line from a hard drive, you have to wait till the hard drive spins around to where that piece of data is. So you would be blocking until the hard drive spun to where that data was. Then when this thing returned, the hard drive was ready and you could read the result right away. Okay. So either way, this thing blocks. An input blocks. The output, the print line doesn't really block. When you send something to the console, it's just, this thing returns right away, and then the output eventually shows up on the console window. Okay. All right. So now this is to me, setting this up with keyboard input and output makes it more visible. We can do experiments with this. If we did this with a file stream here and a file stream here and a file stream here, we can't really watch the file streams happen. But what we want to do now is make this file stream, file stream, file stream, and maybe and see what happens when we do lots of file streams and see if this thing can read massive amounts of data quickly. Okay, so we do want to switch to using file streams, not keyboard input. Keyboard input was nice because you can write little experiments where you can type something, see the output, think about what it did, and you can kind of, it lets you like, it's as if you were running it in a debugger. It kind of lets you think about what the code is doing by watching what you type and how it responds. So if you think, if you look at this picture and think about how the code is going in there, and then the real key is what's inside the parent. But if you think about how this code is set up, you can kind of picture it. But if you just run this program by having it open 3 files and then it runs, then you lose sense of the timing of what's happening. But then you could still run. Now you want to switch to running timing experiments and see if this stuff is really fast or not. Okay. Now, as soon as you switch to doing timing experiments, things start becoming messy. Okay. So here's what I did on my computer. Andrew gave me all his data. Okay. So I've got it on my hard drive. Okay. Now, his data was actually 60,000 files. There were 60,000 files in it. And to do experiments, I took just the 1,000 largest of them. Because, and actually what I did do then, because you really need to do things one step at a time. So here's my sense of doing things one step at a time. I took 1,000 of the files and I combined them into one real large file. So see this file here, data, it's a 2.2 gigabyte file. It's these 1,000 files combined into one huge file. The idea is it's a lot easier to process one big file as quickly as possible than it is to process 10,000 files as quickly as possible. So first, see if you can process one big file as quickly as possible. Then go back to trying to process 1,000 files as quickly as possible. So let's do things kind of one step at a time. Can we process one big file? Okay. Okay. Now I started, the real world is messy as can be. Turns out this data is from Project Gutenberg. These files are a mess. I don't know if you noticed it, Andrew. These files are a real mess. Many of them have binary data in them.
See, yeah, see, I did notice that. That caused me a huge number of headaches.
Thanks for letting me know.
You didn't ask.
Yeah, I didn't
So,
ask.
the tools that I used were things like grep and sed. And I was able to just say to grep and sed, if you see binary data in there, don't treat the whole file as binary data.
Okay, here's what,
just assume it's text.
Okay, here's what was happening. Some of the binary data would screw up a text stream. So some of these files actually hold control Z's in them.
Oh.
A control Z means end of file on Windows. It took me a whole day to figure out why my programs weren't processing the whole file. And then I finally realized that there was binary data hidden in these files, and some of the files actually held control Z's, which were closing the input streams, and so I was mysteriously missing half the data. So I used a program called DOS to Unix to filter these. The other thing was some of these files had Unix line endings, and some of them had Windows line endings. So I thought that was kind of messy too. So I thought I'm going to convert them all to Unix file endings. So I downloaded this program called DOS to Unix, which is a nice little tool which converts batch converts files from Windows line endings to Unix line endings. And it turns out that this tool does the grepping. So it would let me know which files had binary data in them. So I just started deleting them.
So what I did was I used TR to transform carriage returns to new line feeds.
Yeah, so I used DOS to Unix instead of TR because this was a Windows pro. I could download this program exists in versions for both. Maybe TR both. Maybe there is a TR for Windows. I didn't think to look at that. But this program did two things for me. It converted all the line endings to Unix, which helped, and it also let me know when a file had binary data in it. Then I would delete the files that had binary data in it. I just, instead of trying to find the binary data and remove it like you did with grep, I just deleted them. Okay.
Yeah, carriage returns are not carriage returns, but Control Z doesn't really do anything in Linux.
Right, but I'm on a Windows machine, so it drove me nuts.
Well, why are you on a Windows machine?
Well, because that's what the university uses. Okay. So, but it caused me, yeah, it caused a lot of grief to have some Control Z's randomly scattered through these files.
It's probably in the binary data. It's almost certainly not intentionally a Control Z.
Well, yeah, I know. It just by random choice, some of the binary data was Control Z's. Okay.
Mm-hmm.
All right. So but this is a ubiquitous problem in big data. If somebody gives you big data, you can assume the big data is messed up. Everybody knows this. You always have to clean data up. And I was actually being naive and thinking that Project Gutenberg has, yeah, it's a mistake. You keep thinking, you keep making the mistake over and over again. You trust that you got good data from somebody. Like I thought Project Gutenberg, that they would all be Unix files, and it turns out they're a mess. Their
no.
files,
they're Mac, they're Linux, they're Windows.
Some are Mac, some are Linux, some have binary. Okay, so so then I got everything cleaned up, and then I wrote. Here's a question. What's the fastest you can read that data file? Okay, and just do something simple. Count the bytes in that data file. What's the fastest you can read a 2 GB file and count the bytes in it? Okay. Here's a Windows program I wrote. I'll just show you this. We'll work on this. We run out of time. We'll work on this on Wednesday. Count standard in and give it the data file and time it. Half a second.
That's not
impressive.
Right. That's not right.
Yeah, it is. Yep. Half a second.
You're not reading 4 GB a second out of your hard drive.
I'm on a solid state drive.
It'd have to be over PCI Express.
It probably is. Yeah.
SATA's limit is what is it? Less than a gigabyte a second.
It works.
That's the theoretical peak.
Yeah, but it works because now watch. Now I'm buffering. I'm using a buffer to read the data. If I make the buffer smaller, if I make the buffer smaller, see how much slower it got?
Mm-hmm.
The runtime is dependent on the buffer size. The bigger the buffer, yeah. This is we're going to start talking about what it means to buffer I/O and how sensitive this. Notice that this program, I did not change any of my logic in this program, and the program went from taking half a second to taking 6 seconds to do the same thing. What changed the logic of the program was a parameter of the buffer. By the other, I made the buffer. See, there was a big difference. I went from a 256,000 byte buffer to a 1,000 byte buffer. And the program went from taking half a second to taking 6 seconds. But the logic didn't change. Buffering is a real important issue whenever you're doing I/O. If you're not careful about buffering, you won't know what you're doing. And if you change that buffer size, the amount of time for example, let me do something in between. Here's a buffer that's in between the two I just did. Now run the program. And it was actually almost as fast as the large. See, now the buffer is just big enough that it's almost as fast as the one with the really large buffer. Okay, right? Okay, but this is 64 times bigger than it was a minute ago. This buffer is getting to be big enough that the buffer size is stopping to matter too much. As you increase the buffer size, you get to a point where any bigger buffer doesn't help you much anymore. You can't just keep increasing. It's not like tax cuts. If you keep increasing the buffer size, your program won't keep getting faster. At some point, your program gets a little bit faster, but sometimes you get an optimal buffer size. Okay, so what we're going to do is start, since we want to switch to trying to parallelize I/O operations. If we don't know that our I/O operations are as fast as possible, there's no point parallelizing anything. You can't parallelize slow I/O operations. It doesn't speed anything up. So we're going to have to work at how to get fast I/O operations. And this was a C program. And I'm going to do the same thing in Java, and then we'll switch to parallelizing to parallelize code. First, we need to get fast I/O, and we can do parallel I/O. But it doesn't do any good to do parallel I/O until the I/O itself is fast. So that means finding the right buffer sizes. Okay, so there's some. We'll look at the code for that on Wednesday. Okay, and then there's here's some parallel and sequential search. I'm going to search for the word aardvark in all these files. Okay, the word aardvark appears in all those files about 20 times. Okay, so there's a sequential search and a parallel search, but they don't. Turns out right now they run the exact same speed. The sequential search and the parallel search aren't speed. The parallel one's no faster than the sequential one because what's limiting both of them is bad buffering. Okay, so parallelizing doesn't do you any good if you don't have your I/O done right to begin with. So we have to figure out how to do correct I/O. Then we can go and then we'll fix these two over here to get where the parallel one will be faster than the sequential one. But right now, the bottleneck is the I/O to the hard drive. This one's not. They're not buffering properly. Java is notorious for having kind of screwy buffering. It's a little bit tricky to find out the right way to buffer in Java. C is a little bit easier. So we'll talk about buffering, and we'll talk about the buffering in C and Java, and then we'll see that we can make the parallel actually faster than the sequential. Okay, so we should stop. We've gone over time now. Okay, so so the code is on the website. Yeah, the folder. Even this code here, I didn't give you Andrew's data. Is there a way to make the data available to?
Yeah, I gave you a shareable link.
Oh, is it shareable? I can share it to the class?
Yeah, I was wondering why you hadn't posted it.
I hadn't thought about it. I didn't realize those something like, sometimes I'm not sure if it's a link that I can give away or if it's a problem. So it was a link that, so it's a link that I can give I can just put on the website. Okay.
Have you looked over the code that I sent you that accompanied that data?
Yeah, I looked over a little bit of it, but not much of it. I've been busy working on this, and I mean, that's where I got some of these ideas from, but I haven't looked it over. I looked at the shell scripts, but they're not very applicable to what we're doing. So
No, they're a very, very different kind of parallelism than what we're covering.
So the shell scripts weren't much, and then I looked at the shell scripts. I was really curious about how they did things, but their trouble is they're not applicable here. The shell scripts wouldn't be of much use. But the data is real. It's good to have really big data.
And believe it or not, that data, the way that I gave you, had already gone through multiple steps of cleaning.
Yeah, it's still kind of. Yeah.
Oh God.
Yeah, it's really sad how much data can be messed up when you download it. Okay, so I'll put Andrew's link to this data because the code I wrote for the processes I put up on the course website. It's in this folder. Java Futures, but I didn't put the data in there. So I'll put a link to the data, and you could download the data, and then you could play with this code on the. Most of the code in that folder is this stuff that's just playing with 3 streams. Okay, but see this folder here. This is the folder with the code that processes the large amount of data, and this folder here that processes a large amount of data. But I didn't put the data in the folder. I put the code in the folder, but not the data. So I'll put a link to the data up on the website. Then you can try running the code on Andrew's data. Okay. So I'll stop the class here because we've gone over time. And if you have any questions, let me know. Okay. So I'm going to end the meeting. Bye. Good night.
Bye.